Hello. Today we're going to cover divergence theorem. So this is 16.9 from our textbook, and the divergence theorem is the very last thing we're going to learn this semester. In the previous section, we learned Stokes' theorem, and that gave us another way to evaluate line integrals or surface integrals of vector fields that are curl vector fields. So they were like special vector fields. Well, the divergence theorem is going to give us an alternate way to evaluate surface integrals. So the divergence theorem allows us to integrate the divergence of a vector field. Remember what divergence is. It's measuring whether we have a source or a sink or nothing going on. And we're going to integrate the divergence of a vector field over the volume of the solid that's enclosed by the surface, instead of evaluating a surface integral over that same surface. Okay, so this divergence theorem, it has one requirement. It just requires that our solid be completely contained in a closed surface. So that means no missing tops or anything can exist. And the surface has to be positively oriented. Remember that a negative sign can fix the orientation if it's not. And then if our vector field F has components P, Q, and R, and they're all continuous first partials, they all have continuous first partials, then here's what we get. The surface integral of F dot ds is equal to a triple integral over the solid E of the divergence of F and integrated with respect to dV, so it's the differential of volume. And that's it, that's our lesson. So let's go straight to examples. We're going to use the divergence theorem to calculate a surface integral. So right away, before I do anything, I'm going to write divergence. And what it means instead of calculating a surface integral of f dot ds hat, I'm going to use the triple integral over E of the divergence of f dv. Okay. And since we know that the surface integral of a vector field calculates flux, what we're learning now as well is that the triple integral over the solid of the divergence is also calculating flux. So flux of the vector field over the surface S. Okay, so let's see what we have to do to set this up. We have our vector field, f of x, y, z, has components x cubed plus y cubed plus z cubed, and z cubed plus x cubed. And then we have S is a sphere with a center of the origin and a radius of 2. All right, let's work with our vector field first. So we have F. Let's get divergence of F. We have to remember what divergence means. It is going to be the del operator dotted with our vector field. So it means we're looking at the vector with components del del x, del del y, del del z, dotted with the vector field that has components x cubed plus y cubed plus z cubed, and then z cubed plus x cubed. And in a dot product, we multiply like components and then add them. We should get a scalar result. So this will be del del x of x cubed plus y cubed plus del del y of y cubed plus z cubed plus del del z of z cubed plus x cubed. Now I'll go ahead and take those derivatives, and I get 3x squared plus 3y squared plus 3z squared. Okay. All right, so that's not too bad. Nice to work with. Now we need to look at, so this was our integrand. Now we need to look at our differential. So our dv and the surface. And our surface is a sphere with a center of the origin and a radius of 2. So that means it's x squared plus y squared plus z squared is equal to 4. All right. Now, a sphere of radius 2, let's go ahead and draw that. I think my drawings are getting worse the longer the semester goes. It's a good thing it's almost over. So if I integrate over this, I need bounds for everything. And remember, we're dealing with rho phi and theta. We know that rho is the radial arm for the sphere, so it has to be bigger than 0, and it's going out to the edge of the sphere, and this radius is 2. Phi is the angle made with the positive z-axis, and since we're doing a full sphere, it'll start at 0 and it'll go its full domain up to pi. And then theta sweeps us around the z-axis, so that's going to start at 0 and go up to 2 pi. That'll give us a full sphere. And those are the bounds that we need. And so that gives us our dv as well. Now what we need to remember is that in spherical coordinates, dv is going to be rho squared sine of phi, d rho, d phi, d theta. The order there we'll decide in a moment. All right. Then our integrand, it looks like we need to be in spherical coordinates, so our integrand in spherical is 3 rho squared, because 3 times x squared plus y squared plus z squared, we have to remember that x squared plus y squared plus z squared is rho squared, okay? So we're going to be using that for an integrand, these for bounds, and this for a differential. Okay, let's go ahead and set everything up. All right, divergence theorem says that we're going to deal with a surface integral of f dot ds hat by instead looking at a triple integral of the divergence of f dv over e. And we've got all of our bounds and everything else we need in there. So our bounds I'll do in a moment. Our divergence of f is 3 rho squared. Our dv gives us another rho squared, a sine of phi. And I'll go ahead and just do d rho, d phi, d theta. So rho is on the inside, that's 0 to 2. Phi is in the middle, 0 to pi. Theta is on the outside, 0 to 2 pi. I can split this up so that I'm dealing with the integrals separately. And actually, I'm going to move things a bit too to give myself just a little bit more room. All right, this is equal to the integral 0 to 2 pi of d theta. These all get multiplied now because I have separable functions in my integrand and I have constants for my bounds. My phi, 0 to pi, I'll be dealing with sine of phi, d phi. And then I have 0 to 2 for my rho, and then I have 3 rho to the 4th, d rho. All right, the antiderivative of d theta is just going to be theta from 0 to 2 pi. Antiderivative of sine is minus cosine of phi from 0 to pi. And the antiderivative of 3 rho to the 4th will be 3/5 rho to the 5th, going from 0 to 2. All right, first one, 0 to 2 pi for theta gives us just 2 pi. And then in the next one, I have negative of cosine of pi, which is a -1, minus, and then a -1, right? Yeah, so that'll end up giving me a +2 there. And then from the next one, I get 3/5, and then 2 to the 5th is 32. Okay, so it looks like in total, what I've got here is 2 pi times 2 times, that's going to be 96 over 5. And I can put that all together and get 384 pi over 5 for a final answer. Now, I don't know about you, but I'm looking at this and I'm thinking that was, although it was long, it was still much faster than a surface integral over a sphere. So that's pretty cool. Let's do one more. All right, so in this next one, I've got a vector field, f of x, y, z, and I have the same directions. Let's go back up. Use the divergence theorem. Okay, so let's write it. Divergence says that the double integral over s of f dot ds hat will be the triple integral over e of the divergence of f dv. Okay, our vector has components xy plus 2xz. x squared plus y squared, and xy minus z squared. Our surface is the surface of the solid that is bounded by the cylinder x squared plus y squared equals 4, and the planes z equals y minus 2 and z equals 0. Okay, so I'm going to go ahead and calculate my divergence first, since it's the easiest one to do here, and then we'll deal with our surface and the solid that's contained inside of it. So the divergence of f, we're looking at the vectors del del x, del del y, and del del z, dotted with our f vector that has components xy plus 2xz, x squared plus y squared, and xy minus z squared. I go ahead and run my first partials through. I get del del x of xy is just y, plus the del del x of 2xz will be plus 2z. And then plus del del y of x squared plus y squared just gives me 2y. And del del z of xy minus z squared gives me minus 2z. So this sums up to just be 3y. That's not so bad. All right, let's look at our surface. We're dealing with x squared plus y squared is equal to 4. Z is equal to y minus 2, and z is equal to 0. All right, z is equal to y minus 2 has intercepts that are a little bit different from what we're used to. Looks like we're going to be dipping below the xy plane. Sorry. And so the z-intercept is at z equals minus 2, and then the y-intercept will be at 2. So I'm going to draw this on here. Okay. And then the cylinder x squared plus y squared is bounded between this plane and then the plane z equals 0. So we're all below the xy plane. All right, let's get our cylinder drawn on here. I think I'm going too far up on that. Something like this. This is terrible. At some point in my life, I should probably take drawing lessons. All right, so something like this. And this plane will extend on. And here's our cylinder. And it looks like it's bottomed out in such a manner. Okay, I hope that that looks semi-okay. I think I could draw it better if I drew the cylinder first, and then it's something like this. Anyway, forget it. Okay, we have a general idea of what's going on here, so let's hope that that's okay. I can see my bounds for z, right? So this is my lower z, and it is z equals y minus 2. This is my upper z, and it is z is equal to 0. So those are going to be my z bounds. Okay. My x and y bounds are going to come from the cylinder itself. X squared plus y squared equals 4. Okay. So let's see. For dz, we have that z goes from y minus 2 up to 0. And then for dy dx, in some way, shape, or form, we're working with x squared plus y squared is equal to 4. We may switch to cylindrical for that. More than likely we should. So let's just go ahead and recall what this would be. So for cylindrical, we would end up with x is equal to r cosine theta, y is equal to r sine theta, and z would go ahead and get to be z itself. And then we would have, since it's x squared plus y squared equals 4, we would have r going from 0 to 2 and theta going from 0 to 2 pi. Okay. All right, let's see. Our integral, the surface integral over the f dot ds, is going to be the triple integral over E of the divergence, which we found to be 3y dv. And now we're seeing what our bounds are. And it looks like we should have the most inner one be z is equal to y minus 2 up to 0, except we can't let that stay y minus 2. This is z equals r sine of theta minus 2. Okay? Just because we're switching to cylindrical. So I'll put r sine of theta minus 2 for the lower bound, while the other bounds are going to be for r and theta. So we'll go from 0 to 2 for r and 0 to 2 pi for theta. Our integrand, 3y, becomes 3r sine of theta. And then for our dv, we get r dz dr d theta. All right. So let's see what we can do here. Let's go ahead and integrate with respect to z. This is still going to be 0 to 2 pi, 0 to 2, and then I have 3r squared sine of theta, and then my antiderivative of that with respect to z is just z, and z is going to go from r sine of theta minus 2 up to 0. And after that's done, we'll still have a dr and a d theta to handle. Okay, so the evaluation at 0 is 0. We're going to get 0 to 2 pi, 0 to 2. And so 0 minus the 3r squared sine of theta times this r sine of theta minus 2, and then dr d theta. So I need to distribute, gather some like terms, make this look a lot better than it is. Okay, so this gives me the integral from 0 to 2 pi, the integral from 0 to 2 of minus 3r cubed sine squared of theta plus 6r squared sine of theta dr d theta. So I'll go ahead and integrate with respect to r, and this is going to give me the integral from 0 to 2 pi. With respect to r, I end up with minus 3/4 r to the 4th sine squared of theta plus 2r cubed sine of theta, and r is going from 0 to 2. All right, evaluating it 2 to the 4th is 16. So I get, let's see, 16 over 4 is 4, times that negative 3 is going to give me a negative 12. So I get 0 to 2 pi, negative 12 sine squared of theta, plus 16 sine of theta d theta. Okay, so we can integrate the sine squared, but we have to change it. We need to change it to be 1/2 minus 1/2 cosine 2 theta. So I'm going to rewrite this. Number one, I'm going to go ahead and change the order because it drives me nuts to have the negative first. So I have my 16 sine of theta. I have minus 12 times 1/2 minus 1/2 cosine of 2 theta d theta. Okay, that is, if I distribute my negative 12, this is going to leave me with negative 6 plus 6 cosine of 2 theta. All right, so I can go ahead and integrate that. Antiderivative of 16 sine of theta will be negative 16 cosine of theta. Antiderivative of minus 6 is minus 6 theta. The antiderivative of positive 6 cosine of 2 theta will be positive 3 sine of 2 theta, and we're going from 0 to 2 pi. All right, evaluating at 2 pi, my cosines are 1, my sines are 0. So I end up with negative 16 minus 6 times 2 pi plus 0 minus the evaluation's at 0. My cosines are 1, my sines are 0. So I get a minus 16 minus 0 plus 0. And so it looks like in total I'm going to get a negative 12 pi for my final answer. All right, so that's the final divergence value. That's the flux. My flux is negative. Yeah. All right, let's see one more. I think I have just one more for the final semester problem. In this problem, again, we're using the divergence theorem. So we need to remember that the divergence says that instead of dealing with a surface integral over S of f dot ds hat, we're going to handle a triple integral over the solid E of the divergence of f dv. All right, so very first thing, once again, hopefully this is sounding like I'm on repeat because we're going to do the same process. First, we'll calculate our divergence of f. We're looking at the del x, del y, del z vector, dotted with our f vector, which has components e to the y, tangent of z, x squared y, and e to the x cosine of y. And so when I take my derivatives, the derivative with respect to x of the first component is 0. The derivative with respect to y of the second component is plus x squared, and the derivative with respect to z of the third component is 0. So my final divergence value is just x squared. So much nicer than the actual vector field itself. Okay, my surface is the solid that lies above the xy plane, and below the surface, z equals 2 minus x minus y cubed. And so it's below that and above the xy plane, which is z equals 0. And then we're also told that x goes from negative 1 to 1 and y goes from negative 1 to 1. Wow, we pretty much have our bounds. I don't need to draw this. I actually couldn't. Well, that's fabulous. We can go ahead and set up our integral. All right, let's do it. So we have a triple integral. And I know at the very least that my z bounds are going from 0 to 2 minus x minus y cubed. And then x and y are minus 1 to 1 and minus 1 to 1. Don't know which one I want to do first. My divergence is x squared. And then I have to do dz first. I guess we can just do dy next and then dx and see what happens. All right. Antiderivative with respect to z is going to give us, and also I'm gonna actually do this slightly different. I'm gonna go with kind of our old school way of doing things where I break this up into 3 to help myself stay organized. All right, so for my inner one, that's my a, I'm looking at the integral from 0 to 2 minus x minus y cubed of x squared dz. So this just gives me x squared and times z. And z is going from 0 to 2 minus x minus y cubed. So I get x squared times 2 minus x minus y cubed. The 0 gives me no contribution. So this simplifies to be 2x squared minus x cubed minus x squared y cubed. All right, perfect. My b integral, the middle one, will be the integral from minus 1 to 1. And I have my integrand right here. It is 2x squared minus x cubed minus x squared y cubed. And this is going to be dy. So the antiderivative with respect to y, I'll have the 2x squared minus x cubed times y I just treated both of those terms like constants, just to simplify how this looks. Minus 1/4 x squared y to the fourth. And y is going from minus 1 to 1. All right, so this gives me 2x squared minus x cubed times, in that y that's in there, I'm evaluating it from minus 1 to 1, so it gives me 1 minus a negative 1. And then I have my minus 1/4 x squared, and then the y to the fourth gives me 1 minus a negative 1 to the fourth. So that second term is actually going to go off to 0. And the first term does not. It gives me 1 plus 1, which is 2. So I end up with a total of 4x squared minus 2x cubed for my next integrand. All right, so C, the bounds are minus 1 to 1. The integrand is 4x squared minus 2x cubed, and this is dx. So I integrate that, I get 4/3 x cubed minus 2/4, which is a half, x to the fourth, from minus 1 to 1. This gives me 4/3 times, evaluating from minus 1 to 1, I get 1 minus a negative 1 cubed. And I have minus a half, and this gives me 1 minus a negative 1 to the fourth. So the negative 1 cubed, that's going to still be a negative 1, times the negative on the outside gives me positive 1. So I have 4/3 times 2 minus a half times 0, which gives me 8/3. And 8/3 is my final answer. That is the value of the flux, or the divergence, the triple integral of the divergence function. And that concludes this section as well as Calculus 3. If you have any questions at all, please reach out. Happy to answer.